I've invited Andrzej Novak from the CERN Open Lab to talk to us about his work in particle physics, and in particular with the mic architecture. Morning, Andrzej.
Thanks for having us. It's a pleasure.
Great to have you here. Great to have you here. I know you came a long way, and we really appreciate that. Why don't you start out by telling the audience a little bit about Open Lab, because I'm sure a primarily US audience may not have heard of it.
So we work in a collaboration with industrial partners. CERN works in a collaboration with industrial partners. It's called CERN Open Lab. And one of those prime partners is Intel. And we have been working together since 2001 on advancing computing solutions for the Large Hadron Collider. So it's an advanced collaboration on research of advanced computing.
And what is your work in particular?
So I personally focus mostly on parallelism and optimizing not only for multi-core and many-core, but also in-core efficiency. So we do a lot of work on low-level performance. And optimizing performance for Large Hadron Collider software is a really difficult ordeal because it's so complex. It has millions of lines of code, and it's not so easy just to port it to many-core. But we have achieved that.
Well, I've had the privilege of visiting the Large Hadron Collider. I mean, it's truly impressive. Is it possible to share a little bit about that overwhelming experience?
So it's a huge machine that produces a really large amount of data, and we only select a small amount of it, and we keep it. And all the rest is thrown away because we already know it. It's physics that we already know. It operates at a temperature that is cooler than outer space, at 1.8 Kelvin. And I think the best way to introduce it is to show you a video of what we do at CERN.
Let's take a look.
It's the largest machine ever built by man. Backed by the most ambitious scientific collaboration in history. All in the pursuit of unlocking some of the most elemental mysteries of the universe. Including questions related to the elusive Higgs particle, the lone missing particle in the standard model of physics. This is the Large Hadron Collider, built over the course of more than 15 years by the European Particle Physics Laboratory, CERN, in collaboration with the global scientific community. Housed in a tunnel nearly 17 miles in circumference and more than 500 feet beneath the surface of the Earth, the LHC is designed to collide opposing particle beams accelerated to almost the speed of light and capture the results. With collisions taking place 40 million times a second, resulting in a current yearly data production of 15 to 25 petabytes. The testing now underway with the LHC represents not only the world's most ambitious physics experiment, but one of the most demanding and intense compute challenges ever devised.
Well, I have to tell you, as good as that movie is, and that video is, it doesn't compare to actually being there. The physical scale is just overwhelming.
Exactly. So the machine is really huge. You could say that this is the largest machine ever built by man. A really huge ring underground. It's superconducting. And the detectors that we use to capture the data are probably the half of the size of this room.
Yeah.
So in order to process all that data coming in, and in order to sift through it, to select what is really interesting to us, we have underground farms. But the true challenge comes with processing it later. That the real value of the data comes with what comes later. And to that extent, for that we have built the Large Hadron Collider computing grid, and it runs at 250,000 Intel architecture cores.
Whoa. Say that again?
250,000 Intel architecture cores on the Large Hadron Collider computing grid.
So not only is it the biggest machine in the world, I think it's the biggest computer in the world.
So this is a distributed structure, so it's spread across hundreds of data centers across the world, which work in unison in order to be able to process the whole physics complexity that comes with the data.
Okay, so talk to us a little bit about the process.
So the processing takes place in 4 major domains, and out of those 4 major domains, we are working CERN Open Lab is working actively on all of them. And on the video on the screen, you see an example of a simulation framework where we simulate the physics that takes place in the detectors, and then we compare it against the real response of the detectors to understand where the differences are and where could we make a discovery. So one of these workloads is Geant4, a simulation framework, which we have managed to parallelize. It has over 2 million lines of code, and we have worked with Northeastern University to parallelize it and to optimize it, and we have achieved almost a 40x speed up on a 40-core Xeon.
Wow, so almost perfect speed up.
And we really like linear speed ups that the
Don't we all? Don't we all? So I also understand that you've had some early experience with the mic architecture. Can you tell us about that?
Yes, that is correct. We were very excited to find out that Intel is working on the mic because it not only brings a large amount of cores and many threads, but also wide vectors. That means that we can put very advanced and dense workloads on that architecture and develop them very easily. Now, the reason why we were so excited is because Intel has decided to provide the same toolset for the mic as it provides for the Xeon. It means that we could directly apply our experience from the Xeon to the mic, and that way developing for mic becomes a breeze. It's really easy, and we could port our applications in a matter of days instead of expected months, as you could expect with another architecture.
Amazing. Can you actually show us an example of some high-energy physics code?
Yes, let's take a look at the high-energy physics code that Intel helped us visualize. So on this machine, we have a high-energy physics code called the track fitter. So we basically take signals that come in from the detector, and we try to fit the tracks of particles into that response of the detector, and to see where it goes and what is the energy that we deposit in the detector. So we have a single core mic system here that runs only on a single core of a mic. So if we press run, we will see the framework.
I think he means to say he's using one core out of all of the cores on the
Of course.
We don't have a single core version.
This is a 32-core mic, but we only are using one core, so it's a sequential application, right? This is what we have if we don't have any speed up, if we don't try to parallelize our application. So you see that the tracks on the screen are appearing very slowly. It's not really a fast application that can give us a quick response and really the performance that we are looking for.
Well, the power of the mic comes obviously from using all of its cores. Can you show us the full array of what it can do?
Exactly. So on this machine, we have engaged all 32 cores of the mic to process that application. And let's just take a look at that. And you see that the whole workload is processed in a matter of mere seconds, as opposed to minutes, as it would take on a single core. So we achieve a very good speed up, which allows us to get much more out of the hardware, and we are not leaving any performance on the table. And we really do not like to leave the performance on the table.
For sure, not with the kind of workload you've got. Well, so this has shown good scalability. What are your thoughts about scalability in general?
So even before Intel started helping us with this particular example, we have implemented it on our own without talking too much to you guys. And on the screen, you see the scalability graph for that application. So it's a heavily vectorized and heavily threaded workload, which scales almost perfectly with all the cores on the mic. So it means that not only our expertise on the Xeon has paid off, and we were able to get a really good speed up on the mic, but it also means that Intel has delivered a machine that really works very well with very dense code that might not be easy to run in an efficient way.
So where do you plan to go from here?
So we think that it is very important for us to focus on many core scalability, and it is very important for us to make sure that we move forward in this period of time. And that means that we look very much forward to the continued development of the mic technology. We hope to have more cores, and we will take any amount of cores you can throw at us. And we definitely look forward to good scaling of the Xeon.
Hey, if you can use them, we can build them. Thanks, Andrzej.
Thanks, it's been a pleasure.
Pleasure to have you here. Hey, I have one